Okay, so I'm going to talk about the utilization of tape storage for warm data, where warm is defined as you're actually going to read it at some point in time versus cold data where you're putting data into the tape storage system and you're never going to read it ever again. So the question is, how do you build a warm data repository? What are the questions that you need to deal with? The driving motivation around this is the increased data volumes are driving the use of tape systems more actively as warm archives, right? So the problem with tape systems is there are two intrinsic limitations that that you need to deal with. One is that there's a non-trivial amount of time needed to take a tape and mount it into a tape drive in a tape library. That mount time can be up to about 2 minutes per cartridge, right? And the other thing that a system needs to deal with, or utilization of a tape library needs to deal with, is long seek times, right? I should mention that the big difference between the cold archives and the warm archives is you actually are going to need to retrieve the data back from tape, and so mounting and seek times are the issue at hand, right? So dealing with these two intrinsic limitations is what makes building a high performance warm data repository much harder than building a cold data archive. And the bigger issue is it's not just the design of the repository that's important, it's actually how you access the data that is stored in the repository. You can throw all the money you want against a tape library to beef up resources, but if you're gonna if the access pattern to the data is degenerate, then the performance is going to be very bad. So the to deal with the long seek times and the latencies associated with tape mounts, the thing that you're trying to maximize is the amount of data that you retrieve per tape mount, right? And so you can actually calculate the effective utilization of that tape drive, or the effective bandwidth that you can get from a tape drive based on the amount of data that you're going to retrieve per tape mount, right? So the equation on the upper right-hand corner is basically the equation you would use to calculate how much of your tape drive bandwidth is wasted depending on the amount of data you read versus the it's the amount of data that you read, right? So the graph basically is showing the y-axis is the wasted tape drive bandwidth, and on the bottom on the x-axis is the amount of data that you're reading per tape. And so this particular graph is set for LTO9 tape drives, right, and tape cartridges, right? So in order to get 90% of your tape drive bandwidth, you need to be reading at least 480 gigabytes per tape mount for LTO9. The faster the tape drive, the more data that you're going to have to read per tape mount in order to hit a 90% utilization of tape drive bandwidth, right? Now 480 gigabytes is substantially larger than a typical file that one might be reading. So in order to achieve high tape drive effective bandwidth, you're going to have to be reading groups of files back on each tape mount. I call these groups of files clusters in order to standardize on terminology for this particular presentation, right? Now, one of the things that if you want to read back files efficiently, what you need to do is first of all, you're going to have to write your files into the tape in clusters, right? It doesn't help that you read a large amount of data from a tape drive if it's spread all over the cartridge, because you're going to be spending a lot of time seeking to each of the particular files. So you need to be able to identify your file clusters as before you write the data to tape, so that you can co-locate that cluster of files onto a small number of tape drives and contiguously on tape, right? And on the flip side, when you go back to read it, you're going to want to coalesce the individual file requests from that cluster and issue them approximately at the same time or in a short period of time, so that the tape drive system can mount the tape and read everything in one shot, right? Now, one of the issues here is if your files happen to be small and your file clusters happen to be small, then you would need to go even higher into higher level groupings in terms of as in clusters of clusters, right? In order to achieve a data retrieval of over 480 gigabytes per tape mount, right? For now, one of the ways to look at this is that how you write the data is really going to make a difference on how on your performance reading it back. And the analogy that most people might understand here is if you have a database table, there's two ways that you can store your data, either by column-wise or row-wise, right? And so you want to match your access pattern, you want to match your storage pattern with the access pattern, right? And in order to optimize for tape, you really need a single access pattern. You can only, the files on a tape can
3
only,
minutes, Shigeki.
right, the files on tape can only be put into tape one way. So the data there needs to be a dominant access pattern in order for any optimization to work with tape, right? So one of the issues is, how do you get that right pattern? How do you get the data packed onto tape in the right way? The problem here is the way data is ingested, right? The way you can visualize data ingest is to think of the data coming in as a spreadsheet. Files are represented as cells. In the case of the picture on the right, little colored blocks that are coming from the outside, falling from the outside. Columns are file clusters, right? So the cells are arriving at random intervals and vary in size. The columns, new columns appear at random intervals. Columns vary in height. And one of the big issues here is the last cell in the column is not identified, usually in a stream of data coming in, right? So the issue here with optimizing the data when it's being written is that typically the data management pipeline from the data source to the tape drive typically works in units of files, right? File clustering information is not really captured or transmitted easily from the source to the destination tape drive, right? In addition, in order to be able to do optimized writing, you need to be able to buffer complete clusters onto tape, onto disk before you write them out to tape, right? And this is where receipt of a complete cluster becomes important. You need to know how long you need to buffer something before you can push it out to tape, right? And you can do similar things with cluster of clusters, but in most implementations of tape systems in Atlas land, optimization of clusters lags behind optimization of just clusters themselves, right? One of the issues with writing is capabilities and limitations of pipeline components dictate where optimizations can be applied and how easily it is to apply these optimizations. Oops. Right. Regarding reading optimizations, it requires aggregation of file requests by tape. It's a lot simpler than write optimization, since more of the information you need to do read optimization is local to the tape system, right? But in order to do read optimization, it requires file requests to be submitted en masse in a very short period of time so that the system can actually optimize over a large number of requests, right? The problem here, though, is if you do read optimization like this, there are going to be impacts on the downstream consumers. Latencies will be higher because you're going to be submitting a lot of your file requests up front, and it'll take a while for the system to run through that queue of requested files. And then on top of that, the tape system might do a lot of file request reordering, which may have an impact on downstream systems, aka job schedulers, which may not have launched the job or may not be prepared to launch the job at the time that the file comes out, right? And so building high performance warm archives requires additional capabilities of software systems in various parts of the data management chain. Operation of a tape system requires careful management of the full IO lifecycle, right? And it definitely requires participation of data providers and consumers to provide the information necessary for us, the tape system to do the optimization. And also it requires them to interact with the tape system in an optimal way, right? And that's it. Any questions?
Thank you, Shigeki. We've got about 4 minutes for discussion on this topic. You must have something to say on this topic, Kaushik. You're unusually quiet.
Okay. No, I asked my question already from Matt. This Shigeki's talk was quite clear.
I think getting back to the question about the cost impact of accessing data on tape from a QoS system like what Matt was discussing, it really depends on what the readback pattern looks like, and whether or not that readback pattern fits a profile that results in high tape drive efficiency, right? If the readback pattern results in individual files that are small being pulled back from a large number of tapes, then the efficiency, the effective bandwidth that you're going to get out of your tape drives drops dramatically, and that could, in theory, result in an explosion in the number of tape drives that you would need to support the hierarchical storage, right? And so it's the answer to questions of cost is big. It depends on the details.
Thank you, Shigeki. Anyone else? I guess we're done.
All right. So are there any other questions on any of the sessions we've had today? Any additional discussion?
Do we need to have something on the tokens? Are we in good shape for 3.6 in May? But then more importantly, there are other groups outside of Atlas and CMS that also send work to our sites since we contribute to OSG.
So Doug, especially for Bell 2, I think they're a big one for you and David Sanders. We should probably organize some sort of meeting and hopefully get somebody from Bell 2 involved. And we can start sketching out that plan.
So,
but also Dune.
Yeah, Brian and Doug, the other Brian is in contact with Hiro at this point, and we're having a discussion to see where help can be provided. Hopefully this could lead to a meeting as well.
Yeah, that sounds great. And for Dune, we are working with Steve Tim. He's the one that runs their front end, which is responsible for creating the token.
And technically, I don't know the front end, but there's somebody else in the same group as me that does.
Ah, sure. But yeah, we are working with Steve and team to get them along to submitting with tokens.
I did post a in this session because it was the Atlas session.
Sure. But I did post a link. I'll post it again in the chat. We are trying to keep track of all the different VOs that are submitting with tokens. And we're trying to keep that up to date. So if you see a collaboration in this list that you support and they are not submitting production tokens yet, let them know that this is going to be a problem for you, and also let us know.
And I see Andy has his hand up.
Yeah, so I'll just bring this up because it came up just recently. It's going to be a longer term issue that we have to resolve. This is tokens for storage. And people have been pointing out that there are semantic differences between WLCG tokens and Psi tokens in terms of permissions. Currently we have a submission that basically makes Psi tokens compatible permission-wise with WLCG tokens. And I have to, and haven't yet been able to catch someone's attention of saying, is this the road we want to take? Because that's a significant change, right? So I'm just putting it on the table as this is going to be a problem.
Andy, I'm not entirely sure I understand what exactly the problem is. I know there is that compatibility later. Extra D depends on the Psi tokens CPP library, right?
Right, and that perfectly works, right? It's not a problem. The problem is when it comes to authorization, how do you interpret the claims? One incompatibility is in order to list a directory, you have to have a claim that you are capable of listing a directory, even though you can read any file that directory. Now that's compatible with Unix. That's exactly what Unix does in terms of permissions. But that's not what the way WLCG does permissions. Permission for them means if you're able to read a file in a directory, you can also list the directory. And you can see that's a semantic difference between what a WLCG token expects when it makes claims and what a Psi token expects when it makes claims. And that's where the incompatibility becomes real. You see what I'm talking about?
Yeah, I don't know if you've brought this up in the WLCG authorization working group. That's probably the right idea, the right place to start asking these type of questions.
Right. So, but we have outstanding pull requests, right? That try to correct this, and we're saying we don't know if this is appropriate or not, right? Because there's nobody there to tell us, oh yeah, this is okay, you can do this.
Yeah, so I think this is appropriate to suss out with the authorization group, and
All
then
right,
you
so-
can act on the PRs.
Okay, can you just send me, not now, I mean, not, we can take this offline, right? To basically make sure that I know the right people and where to go.
Right.
There's an email list, Andy. I'll send you the CERN group stuff.
Okay,